Hi there! After publishing a short on winding a small toroidal transformer, I got several requests for a video showing how to design one. And since you asked, here is the video. Have fun! Before getting into the formulas and calculations for designing a toroidal transformer, it is better to glide over the physics concepts that allow us to design and build such electric machines. The physics principle according to which a transformer works is called Faraday's law. This principle has to do with a correlation between the current flowing through the wire of a solenoid and the magnetic field generated inside of it. And it works in both directions. If we apply a variable voltage to the leads of a solenoid, a variable current will be generated, and such a variable current will generate a variable magnetic field inside the solenoid. Also, if we take another solenoid and we submerge it inside the variable magnetic field of the first solenoid, a variable voltage will be generated at the leads of such solenoid, and if we apply the load to them, a variable current will flow. The most important part correlates the intensity of the magnetic field with the sectional area of the solenoid. The magnetic field through a sectional area is called magnetic flux, and the flux density and intensity correlates directly with the amount of current that the created voltage can sustain. To understand the concept of flux, think of a pipe with a specified sectional area where water flows inside of it. The larger the area, the larger the flux of water going through. Now, if we insert a ferromagnetic material inside the solenoid, the intensity of the magnetic field will be hundreds of times stronger. We call the ferromagnetic material inside the solenoid core. We call the solenoid used to generate the magnetic field primary coil, and we call the second solenoid secondary coil. This is the working principle of the transformers, and we can do even more. We can force the flow of the magnetic flux to turn around on itself so we don't waste any of it, thus reinforcing even more the transfer of energy from one solenoid to another. Here is how it works. We apply a voltage to the solenoid on the left, which ends up generating a current in the wire. The current generates a magnetic field through the whole magnetic core, imprisoned by it, so we don't lose any part of it. Almost. And that creates a magnetic flux that moves along the path identified by the core. The variable flux induces a voltage into the solenoid on the right. If we connect a load, for example a resistor, to the leads of this solenoid, we obtain a current, even though the two solenoids are not electrically connected to each other. Talking about transformers, the solenoid on the left is called primary, which is the coil where we inject the electric current. The solenoid on the right is called secondary, which is the coil where we extract the induced current. The number of turns in the first solenoid and the number of turns in the second solenoid are also correlated. The ratio between the number of turns in the primary and the number of turns in the secondary is directly proportional to the ratio of the voltage applied to the primary and the voltage induced at the secondary. Therefore, we can calculate the voltage at the secondary if we know the voltage at the primary and the number of turns at both the primary and the secondary coils. And this formula is at the base of any transformer calculation. This other formula instead correlates the voltage with the magnetic flux and the number of turns. In here we have Kf, that is the waveform coefficient, which we'll talk about later. F is the frequency of the applied variable voltage, N is the number of turns of the solenoid or coil, AC is the sectional area of the magnetic core, B is the magnetic flux density, and such formula is in fact the result of Faraday's law applied to our case. More on that later. Now that we know that a transformer is made of two windings and one magnetic core in the shape of a closed loop, let's see what kind of ferromagnetic material we can actually use to make the core. Well, the thing is that the materials we can use for the cores physically depend on some electromagnetic parameters that we need to take into account when designing a transformer. The parameters are the range of frequencies of the involved voltages and currents, the intensity of the currents, and therefore the magnetic flux density, the max power at which the transformer is supposed to operate. For that, we distinguish two main categories of materials that we can use to make a core: ferrite cores and iron silicon cores. Ferrite cores are used for high-frequency applications, from audio frequencies up to radio frequencies. Iron silicon cores are used for power applications, with frequencies around 56 Hz. And that depends on the capability of these materials to be able to handle the appropriate amount of magnetic flux without saturating, and the capability to conduct the right amount of flux without dissipating too much energy, property that is affected by their magnetic permeability μ. Regardless of the application, the involved power, and the frequencies, all transformer calculations are basically regulated by the same formulas. We will now go through all the basic calculations for the use case of a power transformer, but keep in mind that the same formulas and the same procedure can also be used for audio transformers and for RF transformers. Before we start the procedure, we need to define the specifications for the transformer we want to design. You'll find most of them obvious, given that what we have said already. Number 1 is the input voltage, which we will represent with Vi. Number 2 is the output voltage, which we will represent with Vout. Number 3 is the output current, which we will represent with Iout. Number 4 is the frequency, which we will represent with the letter F. Number 5 is the application for this transformer, either power or audio or RF. Number 6 is the number of phases, which we'll keep to 1 for this tutorial. Multiple phase transformers need a discussion on their own, and the most of us, interested only in electronics, won't even care about them. Here is the general procedure necessary to design a toroidal core transformer. Step number 1. Calculate the power that will be handled by the transformer. This is very important for two reasons. 1. We need to size the wires section so that they will be able to handle the needed current. 2. We need to figure out the sectional area of the transformer core, which depends on the power that needs to be moved. The first reason is obvious because although the specifications give us the amount of current at the secondary, we still need to calculate the amount of current at the primary, and that needs to be done through the power. The second reason is tied to the magnetic flux intensity in the core. The flux intensity depends on the sectional area, and the amount of power that can be transferred from the primary coil to the secondary coil is proportional to the amount of flux. The more the power, the more the flux. The more the flux, the larger the sectional area, according to Faraday's law. To calculate the involved power, we just need to multiply the voltage output by the current output. And that is expressed in VA or voltamperes, or voltamps, since we are dealing with alternate currents. Step number 2. Adjustment of the power because of the transformer efficiency. The problem is that not all the power at the primary is going to be transferred to the secondary. and that's because the core itself will dissipate some of the power, mostly because of the eddy currents that the variable magnetic field will try to induce in the core. The core material is designed in such a way to present a reasonable amount of magnetic permeability while at the same time a high electrical resistance. And the high resistance reduces the eddy currents. Still, there will be some loss of power, and the core will warm up because of that. Here is the formula that adjusts the power for the efficiency. In here, VA is the actual power we need, P out is the power calculated previously, and eta is the efficiency, which is a pure number between 0 and 1. In general, we can say that for a well-designed transformer with toroidal core, it is safe to assume an efficiency around 90%, or eta equal 0.9. Step number 3. Calculation of the core area product. But what is this entity? Well, this has something to do with the geometry of the core. Basically, it is the product between the sectional area of the core, AC, and the area of the empty space surrounded by the core, which we call AW, or window area. Here is the formula. This entity correlates directly with the power VA that we calculated in the previous step. The correlation is through the Faraday's law, adjusted to consider the mechanical measurements, the power of the transformer, and the maximum amount of flux that the core can handle without having its magnetic capabilities altered forever. You can compare the max flux that a core can handle with the max amount of current that can flow through a wire. The max current depends on the sectional area of the wire and the material, whether it's copper or aluminum or a different compound. For the magnetic core, the max flux depends on the sectional area of the core and on the material of which it is made. The window area comes into play when you consider the length of the path the flux has to go through, like in the case of the length of the wire a current has to go through. It also comes into place when considering the space the wire will occupy when winded around the core. These entities are correlated through the following equation. In this equation, VA is the adjusted power we calculated in step 2. Kf is the waveform coefficient that depends on the shape of the voltage applied at the primary. Bmax is the max flux density expressed in Tesla. J is the current density through the secondary. Ku is the winding utilization factor. The waveform coefficient comes out from the resolution of the integral in the Faraday's law. It is substantially the ratio between the RMS value of the voltage divided by the average of the half wave of the voltage, multiplied then by 4. For example, for a sine wave, such value is about 4.44, while for a symmetrical square wave, since the RMS and average values are the same, Kf is only 4. The current density J is the ratio between the current in the wire and the sectional area of the wire, and it is expressed in amp per square millimeter. Ku, the winding utilization, is directly correlated with the space occupied by the wire when winded around the core, and therefore depends on its geometry. An acceptable value for a toroidal core is around 0.4. Given all of that, we can now calculate the core area product rearranging the previous formula in this way. The factor 10 to the power of 4 converts the results in centimeters to the power of 4, which is how this entity is expressed in the datasheets of the magnetic cores. And this concludes the calculations on the third step. Step number 4. Select the toroidal core we would like to use. In this step, we need to consult the manufacturer's datasheets for toroidal cores. They list various core sizes with their corresponding AP value. If the datasheet does not report that value, however, you can use the window area AW and the cross-sectional area AC and calculate the AP value as AP equals AW times AC. The datasheets also provide a value for Bmax. At this point, we apply the equation for the determination of the AP value with the new value of Bmax, and if that is smaller than the one we are using, go back to that step and recalculate the needed AP using the given Bmax value. Then search for a better core. This step may take a while, as you'll have to try multiple times until you find the core you need. Step number 5. Calculate number of turns per volt, or TPV. The number of turns per volt is calculated using this formula, where AC is measured in square centimeters, Bmax is measured in Tesla, F is measured in Hertz, Kf is equal to 4.44 for a sine wave. If the datasheet you are using provides Bmax expressed in Gauss, you will have to convert it into Tesla, knowing that 1 Tesla equals 10,000 Gauss. Step number 6. Calculate the number of primary turns, NP. Now that we have the number of turns for 1 volt, we can calculate the total number of turns in the primary by multiplying TPV by Vin. Step number 7. Calculate number of secondary turns, Ns. This calculation can be achieved in 2 different ways. Choose the one that you like the most. First option. Apply the same equation used to calculate the primary turns, but add 5% to adjust for losses during the transformation process. Second option. Use the known ratio of voltages to calculate the ratio of turns and add the same 5% correction. Step number 8. Calculate primary current IP. The current at the primary needs to provide the power needed at the secondary. Step number 9. Select wire gauges of primary and secondary coils. Based on the max amount of current flowing in the primary, select the most appropriate wire gauge to prevent coil overheating. Then do the same for the secondary coil. We will call the sectional area of the primary wire AP wire, and we will call the sectional area of the secondary wire AS wire. Step number 10. Estimate the winding space. This is a necessary step to make sure that we can fit both coils on the core we have chosen. In particular, we need to make sure that there is enough space in the toroidal window to fit all the turns and to leave some space in the center. The total wire area for the primary will be equal to NP times AP wire. The total wire area for the secondary will be equal to NS times AS wire, and the sum of these quantities, plus the insulation area, should not exceed about 40% of the window area AW. If that cannot be done, we will need to go back to step 4 and select a larger toroidal core, and then redo all the calculations starting from there. And there you have it, the complete procedure to calculate a toroidal transformer. You can use this procedure to design your own transformers, either for power supplies or for small circuits that require a similar component to perform some kind of task. For example, an audio transformer to adapt the impedance between two elements in the audio chain, or maybe a small transformer to create your own boost converter, and so on. Just make sure, once you have done all your calculations, to go through them more than once and make sure everything is right. Especially with power transformers, a wrong calculation can cause a lot of damage, or even cause harm to yourself and/or others. It is your responsibility to make the proper calculations to avoid damage to objects and to people. I'll see you in the next video, and in the meantime, happy experiments!